the James Webb Space Telescope's first images of the distant universe shocked astronomers. Is the discovery of unimaginably distant galaxies a mirage or a revolution? Rowan Naidu was sitting at home with his girlfriend when he found the galaxy that nearly broke cosmology. As his algorithm dug through early images from the James Webb Space Telescope, JWST, late one night in July, Naidu shot to attention. It had sifted out an object that, on closer inspection, was inexplicably massive and dated back to just 300 million years after the Big Bang, older than any galaxy ever seen before. I called my girlfriend over right away, says Naidu. I told her, this might be the most distant starlight we've ever seen. After exchanging excited messages with one of his collaborators with lots of exclamation marks, Naidu got to work. Days later, they had published a paper on the candidate galaxy, which they named Glass Z13. The internet exploded. It reverberated around the world, says Naidu. Even Captain America would share the story on Twitter. The extraordinary discovery of this galaxy, just weeks into JWST's full operations, was beyond astronomers' wildest dreams. JWST, the largest, most powerful observatory ever launched from Earth, was custom-built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference, chilled within striking distance of absolute zero by its tennis court-sized sunshade, the telescope's giant segmented mirror and exquisitely sensitive instruments were designed to uncover never-before-seen details of cosmic dawn. This is the scarcely probed era, no more than a few 100 million years after the Big Bang itself, in which the very first stars and galaxies coalesced. How exactly this process unfolded intimately depends on a witch's brew of exotic physics, ranging from the uncertain influences of dark matter and dark energy to the poorly understood feedbacks between starlight, gas and dust. By glimpsing galaxies from cosmic dawn with JWST, cosmologists can test their knowledge of all these underlying phenomena, either confirming the validity of their best consensus models or revealing gaps in understanding that could herald profound new discoveries. Such observations were supposed to take time. Initial projections estimated the first galaxies would be so small and faint that JWST would find at best a few intriguingly remote candidates in its pilot investigations. Things didn't quite go as planned. Instead, as soon as the telescope's scientists released its very first images of the distant universe, astronomers like Naidu, at the Massachusetts Institute of Technology, started finding numerous galaxies within them that, in apparent age, size and luminosity, surpassed all predictions. The competition for discovery was fierce. With each new day, it seemed, claims of yet another record-breaking earliest known galaxy would emerge from one research group or another. Everyone was freaking out, says Charlotte Mason, an astrophysicist at the University of Copenhagen. We really weren't expecting this. In the weeks and months following JWST's findings of surprisingly mature early galaxies, blind-sided theorists and observers alike have been scrambling to explain them. Could the bevy of anomalously big and bright early galaxies be illusory, perhaps because of flaws in analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or, just maybe, were they the first hints that the universe is more strange and complex than even our boldest theories had supposed? At stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. JWST's early revelations could be poised to rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies but also our own existence here, in the familiar Milky Way. You build these machines not to confirm the paradigm, but to break it, says JWST scientist Mark Makorian, a senior advisor for science and exploration at the European Space Agency. You just don't know how it will break. One might say JWST's observations of early galaxies have been billions of years in the making, but more modestly they trace back to the Space Telescope Science Institute, STSCI, in Baltimore in 1985. At the time, the Hubble Space Telescope was still 5 years away from launching on a space shuttle. But Garth Illingworth, then the deputy director of the STSCI, was surprised one day when his boss, STSCI's then director Riccardo Giacconi, asked him to already start thinking what would come after Hubble much further down the road. "I protested, saying we've got more than enough to do on Hubble," Illingworth recalls. But Giacconi was insistent. "Trust me, it'll take a long time," he said. So, Illingworth and a handful of others got to work, drawing up concept ideas for what was then known as the Next Generation Space Telescope, NGST, later renamed to JWST after a former NASA administrator. While Hubble would be transformational, astronomers knew its capabilities would be limited by its observations in visible light. As light from a very distant galaxy travels across the cosmic abyss, it is stretched by the expansion of the universe, a broadening of wavelengths known as redshift. The higher the redshift value, the more stretching the light has experienced, and thus the more distant its source galaxy will be. Redshifts for early galaxies are so high that their emitted visible light has stretched into infrared by the time it arrives at our telescopes. This is why Hubble could not see them. The NGST, for comparison, would observe in infrared, and would boast a very large, and very cold, starlight gathering mirror, allowing it to peer much deeper into the universe. Everybody realized that Webb would be the telescope for looking at early galaxies, says Illingworth. That became the primary science goal. The need for the telescope was highlighted in December 1995. When astronomers pointed Hubble at a seemingly empty patch of the sky for 10 consecutive days. Many experts predicted the extended observation would be a waste of resources, revealing at best a handful of dim galaxies, but instead the effort was richly rewarded. The resulting image, the Hubble Deep Field, showed the empty spot was actually filled with galaxies by the thousands, stretching back 12 billion years into the 13.8 billion year history of our universe. There were galaxies everywhere, says Illingworth, now an astrophysicist at the University of California, Santa Cruz. The Hubble Deep Field showed that the early universe was even more crowded and exciting than most anyone had expected, offering observational treasures to those who took the time and care to properly look. Yet, impressive as Hubble's deep field was, astronomers wanted more. After more than 2 decades of labor at a cost of some $10 billion, JWST finally launched on Christmas Day 2021. By July 2022, the telescope had reached its deep space destination, and its instruments had been put through their paces. Its long-awaited first year of science observations, known as Cycle 1, could begin. A portion of the telescope's early time was devoted to high-impact programs across a range of disciplines from which data would immediately be made public. 2 of those, CEERS, the Cosmic Evolution Early Release Science Survey, and GLASS, the Grism Lens Amplified Survey from Space, would each independently spend dozens of hours looking for distant galaxies in the early universe by staring at separate small portions of the sky. Not much was expected. Perhaps a slightly more ornate version of the Hubble Deep Field, but nothing more. Stephen Finkelstein from the University of Texas at Austin, the lead on CEERS, says extremely distant galaxies were only predicted to pop up after a few cycles of data from multiple programs. Instead, much to the surprise of astronomers, such galaxies came into view immediately. Hubble's record for the most distant known galaxy had been GNZ11, spotted in 2015 at a redshift of 11 thanks to a 2009 upgrade to the telescope that enhanced its modest infrared capabilities. A redshift of 11 corresponds to a cosmic age of about 400 million years, a point at the brink of when galaxy formation was thought to begin. But from the very first GLASS data, 2 teams, one led by Naidu in that breathless late-night discovery, independently found a candidate for a more distant galaxy, dubbed GLASS Z13, at a redshift of 13, some 70 million years farther back in time. In their thirst for quick results, the researchers relied on redshift estimates derived from simple brightness-based measurements. These are easier to obtain, but less precise than direct measurements of redshift, which require more dedicated observation time. Nonetheless, The simplified technique can be accurate, and here it suggested a galaxy that was unexpectedly bright and big, already bearing a mass of stars of 1 billion suns, just a few hundred times less than that of the Milky Way, despite our own galaxy being billions of years more mature. This was beyond our most optimistic expectations, says Tommaso True, an astronomer at the University of California, Los Angeles, and the lead on glass. The record did not last long. In the following days, dozens of galaxy candidates from Sears and Glass sprung into view with estimated redshifts as high as 20, just 180 million years after the Big Bang, some with disk-like structures that were not expected to manifest so early in cosmic history. Another team, meanwhile, found evidence for galaxies the size of our Milky Way at a redshift of 10, less than 500 million years after the Big Bang. Such behemoths emerging so rapidly defies expectations set by cosmologists' standard model of the universe's evolution, called lambda CDM, LCDM. This model incorporates scientists' best estimates for the properties of dark energy and dark matter, which collectively act to dominate the emergence of large-scale cosmic structures. Lambda refers to dark energy and CDM refers to dark matter that is relatively sluggish, or cold. Even if you took everything that was available to form stars and snapped your fingers instantaneously, you still wouldn't be able to get that big that early, says Michael Boylan Colchin, a cosmologist at the University of Texas at Austin. It would